Good evening, everybody, and welcome to our April 2022 meeting of Guildford Astronomical Society. Welcome to people far and wide. To my knowledge, we have at least one of our meetings in one of our members in Geneva. I haven't seen, but we have a member who occasionally comes in from North Carolina, but he doesn't seem to be with us today. Anyway, welcome. And I'd like to introduce Professor Nial Tanvir. He's a British astronomer at the University of Leicester, whose research specialisms are the extragalactic distance scale, galaxy evolution, and gamma ray bursts. He's featured in various TV programs, including The Sky at Night, hosted by Patrick Moore, and Horizon. He studied maths and physics at Durham University, graduating in 1986, was awarded a PhD from the same institution in cosmology, and subsequently held a doctoral position at Durham before joining Cambridge University's Institute of Astronomy and later the University of Hertfordshire. He was appointed Professor of Astrophysics at the University of Leicester in 2006. Nial headed the international team that discovered the infrared afterglow of GRB 090423, which was detected on April the 23rd, St. George's Day, 2009. And that's the most distant source recorded to that date. In 2013, he led a team that discovered so-called kilonova emission accompanying GRB 130603b, which provided the first direct evidence that short duration gamma ray bursts are created by merging compact sources, either to neutron stars or a neutron star and black hole. In 2002, he was a member of the research group which won the European Union Descartes Prize for their pioneering work on gamma ray bursts. He was awarded the Herschel Medal of the Royal Astronomical Society in 2019. Nial, the floor is yours.
Okay, great. Thank you. Thank you for the very kind introduction as well.
And now I must relinquish my grasp on the.
Okay, so does everyone see my first slide then? I'll assume so, unless someone shouts out. Okay, so great. What I am going to talk to you about then are some of those topics that were mentioned there in that preamble. Short duration gamma ray bursts, kilonovae, and gravitational waves. All, as we'll see, I think tremendously interesting things. I guess there's some people here that are quite expert and may know already quite a lot about some of these things, but I think the story that we're trying to tell here is quite a kind of involved one, and so some of the steps and connections may still require a little thinking about. But I'll try and introduce all of the topics as we go along, in fact, and so that we start to see how they all relate together. Now, there could be a subtitle of this talk, and that if we had one, it would be "If it glitters, it may be gold," and we'll see where that ties in. This took me ages to generate this in PowerPoint, I can tell you, getting curved writing. Okay. So yeah, what's it all about? So what we're going to be looking at are three very long-standing astrophysical problems or challenges, if you will, and the breakthroughs that have been made, particularly in the last few years, in resolving them, and the fact that these problems all have a sort of common solution or commonality to their solution. So the first one in the title is the short duration gamma ray bursts. You may or may not know what they are. We will talk about what they are, but they're basically very, very violent and exotic explosions. The bit about gold comes in the second point here, because the other puzzle that we want to address is the origin of the heavy chemical elements. So we don't frequently think very much about the chemical elements that exist all around us. One just assumes what's there is there, but in fact, from an astrophysical point of view, we would like to know where all of the different chemical elements that exist in nature were originally created. So they didn't arrive in the Earth just from nowhere. They had to have been previously made somewhere in the cosmos. And in particular, there is a whole class of elements that we call the R-process elements, which I'll try and explain as we go on, but that includes elements like gold and platinum, things that we're pretty familiar with, rare elements certainly, but there are very many of them. And their origin, as we'll see, has been a mystery for many decades, going back to the 1950s. And then, in a sense, an even more long-standing challenge has been that presented by so-called gravitational waves. These were predicted, as we'll see in a moment, by Einstein back in 1916, but it wasn't until sort of 2015 that the first evidence was found showing that they really do exist in nature. And so I need to tell you about all these different things before we can draw the themes together. And I'm going to start off and go through them in kind of reverse order. So let's first of all introduce the great man himself, Albert Einstein, there on a visit to Cambridge, sitting there with Arthur Eddington. And he can tell us, what's he going to tell us? That gravity is not a force, in fact. It's a consequence of the warping of space-time. So that is the view, the mathematical view that is encapsulated in the theory of general relativity. And so it's really quite a break from the old Newtonian view of gravitation, but that's where we are. And so Eddington can elaborate, and he can say that so falling objects follow straight lines through curved space-time. So we're now doing away with the idea of force, and we're saying that instead somehow objects moving through space under what we call the action of gravity end up following curved paths because the space-time is curved, and the time aspect is important. It's not just, as this sort of cartoon picture tries to illustrate, simply a curvature of space. That's something we can kind of wrap our heads around a little bit, because we could imagine a sort of curved table and, you know, curved snooker table and rolling balls around it, and they would follow sort of curved paths. But the true theory is more complicated than that, because it does have this this effect on time as well. And so this, in some sense, is just a useful way of giving us the feeling that we're starting to understand the theory, where we can imagine rolling balls on this curved table and they would follow those different paths as we see there. However, for our purposes, the more interesting thing is the fact that Einstein realized that if space-time exists in this sense, then there should also be ripples carrying gravitational energy, that if masses, which are what is curving your space-time, if they were to change rapidly, then those changes have to be reflected in the curvature of space-time, and the changes can only travel at the maximum speed, the speed of light, and therefore there must be waves which transmit those changes, so-called gravitational waves. And of course, historically, we know that Eddington took great interest in this new theory, very quickly mastered it, in fact, and was instrumental in running the expedition to observe the eclipse in 1919, which of course was regarded as the definitive test of general relativity at the time. Okay, so let's have a little look at another schematic picture then of what these gravitational waves would look like. What we're imagining is an ideal source of gravitational waves is going to be something like two black holes orbiting around each other. As they emit gravitational waves, and we'll see the waves themselves in a minute, the orbit loses energy, and so the holes become closer and closer together until, as we'll see in a moment, they're going to merge. And as they get closer and closer together, they also start to orbit more and more rapidly, and so the gravitational wave intensity increases and the frequency increases, and we can see that in the little plot running along the bottom there. And so in just a moment, and the whole thing slows down here, you can see the time scale is very short. So we're down here at milliseconds, and black holes, when we teach them to undergraduates, are always nice spherical things. In truth, of course, They can be more than that. They can, at very least, rotate. But in fact, if you merge two black holes, as we have in this instance, then they can be deformed. And mathematically, that's a very hard thing to study, but we know it happens. And schematically, we can see the gravitational waves there rippling out through the universe. So that whole two-dimensional surface we saw there, we have to imagine that as somehow representing our three-dimensional space. And in fact, as we said, the four-dimensional space-time as well. Okay, so how would we detect such gravitational waves? There is a long history to this. Again, in the 1960s, the first attempts were made to detect gravitational waves using, in fact, very large aluminium blocks, which were, it was hoped, would be set into vibration by the passage of gravitational waves. We've come to realize that they were never, despite some claims that they had made some detections, they were never going to be sensitive enough. And instead, the modern detectors use these very large scale interferometers, and we can see an aerial picture here of one of the so-called LIGO interferometers. You've got two arms there that have vacuum tubes in which two lasers are fired down to the end from the central facility in the middle, off mirrors back and bounce backwards and forwards many times. And the whole idea is that if there was no change in the relative lengths of those two arms, then, as we'll see in a minute, you engineer your interference system so that you would always get destructive interference on one detector, so you would see no light. Whereas if there are very small changes in the relative lengths of the two arms, which might be brought about by the passage of some gravitational waves through the Earth and through your apparatus, then that can lead to a very small amount of constructive interference, and therefore you would get a certain amount of light on your detector. So we'll illustrate that then with this, again, this nice little schematic cartoon there, and we can see that should our two arms, which are like kilometers long, 4 kilometers long in this particular case, should they change slightly, then it's going to lead to this this element of constructive interference, as we'll see. I guess one should say that, of course, any kind of tremor is going to result in such changes in seismic activity, etc. So this is something that one has to do very, very carefully and isolate your equipment as well as you can. But that's the basic principle of the method. And you say, well, okay, that's pretty impressive. How impressive is it? Turns out it's very, very impressive, because the kind of fluctuations that they're talking about are something like 1,000th of the size of a proton. So you've got these two arms which are 4 kilometers long, and you're looking for changes in their relative lengths at a scale of sort of 10 to the minus 18 of a meter or so. So it's incredibly tiny. Nonetheless, the latest generation of those interferometers in 2015, when it was turned on, in fact, just before it was officially turned on, but while it was just doing the final engineering tests before the official turn on, made, in fact, what turned out to be the first detection of a gravitational wave. You can see the famous signals that were detected, and these, of course, led to Nobel Prizes and everything else. And in this instance, what was determined was that this gravitational wave was produced indeed by the merger of two fairly massive but stellar mass black holes at some fair distance across the universe. But the signature that was seen was exactly what had been anticipated all these years, and therefore it was regarded as a very confident discovery. And one of the reasons that one had confidence was in fact that there were two of these LIGO detectors, one in Washington State, one in Louisiana, so separated by a couple of thousand miles. And all that seismic activity that I mentioned and similar things which might lead to spurious signals in your detector, one hopes that if you separate two detectors by a couple of thousand miles, you hope that they're not going to be affected by the same kind of local noise effects of that kind. And so the fact that one saw essentially the same signal in both of those detectors was what gave very great confidence that indeed the signal was real. Okay, well, those detectors, and indeed the Virgo detector near Pisa in Italy, have now been working on and off for another 6 or 7 years. The way these things work is that they tend to have an on time of about a year or so, and then they will turn the detectors off while they upgrade various components and make them more sensitive, and then turn them back on again. And in the time up to date, the number of systems that have been found is shown in this figure here. And what we see is that in most cases, the large majority of detections have been of binary black holes, where two smaller black holes join together to make an even bigger one. And so typically you're talking 10, 20, 30 solar masses for the black holes that you start with, and then they merge together to get something that's 50 to 100 solar masses typically. But occasionally, and they're denoted here by little orange blobs instead of blue ones, you get a different kind of object taking part in these mergers, and that's a neutron star. So neutron stars are going to feature throughout this story, but we'll introduce them here for the first time. What we see is that the neutron stars are typically lower masses, more like 1 to 2 solar masses. There are a few objects which we're not quite sure whether they're neutron stars or black holes, and those are both blue and orange there. And of course, if you merge two neutron stars, you have the possibility, quite likely, that you might make a black hole in that merger, but it's also possible you might just make a heavier neutron star. And of course, one might merge a neutron star with a black hole. So neutron stars are the most dense kind of objects that we know of in the universe, short of black holes. So they're the sort of last stage that matter can reach before it collapses entirely into this sort of mathematically perfect kind of object, which is the black hole. So neutron stars are altogether more complicated and messier things than black holes, but in some senses, at least for this story, they're going to be the more interesting thing. Right, okay, so that was gravitational waves. Now let's have a little think about those R-process elements, which I said to you, they represent a lot of the heavy elements in the periodic table, and we're interested to know where all the elements in the periodic table came from. So here's a periodic table full of familiar and less familiar elements. Of course, if you if you're a keen watcher of Eggheads or those sort of quiz shows, you'll no doubt have memorized a whole bunch of the weird ones down at the bottom, and so that's all good stuff, because many of those are the ones that we're interested in these R-process elements. So if you were to ask the question, where do the chemical elements come from? Well, modern astrophysicists have some pretty good ideas about many of them. In particular, we think that the simplest, hydrogen and helium, which is just one proton, and then that's the hydrogen nucleus, and the 2 protons and 2 neutrons, which is the helium-4 nucleus. Those are the simplest elements that we find in nature and the most abundant by far. And we believe they were created essentially in the Big Bang. So the material that came out of the Big Bang comprised largely just these 2 simple elements, with a smattering of other elements, but very little. And so where have all of the other heavier elements come from that we're familiar with? And so, we know that we are made up of carbon, oxygen, nitrogen, et cetera, all of those elements must have come from somewhere. And it was realized when the first work was done in understanding the power of the power source of stars, it was realized that that was nuclear power, that nuclear fusion of essentially starting with hydrogen and creating heavier and heavier elements that way in the cores of stars, that was going to give us an answer to the question of the origin of many of these elements that I've listed above. And in particular, a massive star like this one, towards the end of its lifetime, it's used up, it's cooked all of the hydrogen in its core, but it's also cooked successively certain elements in outer layers beyond the core. And one ends up with this sort of onion shell structure with still hydrogen, helium in the outer envelope, but then successively heavier and heavier elements as you work your way in towards the core, which is finally going to be made up of iron and nickel and those kinds of elements there in the center. And of course, what happens if this is a massive star at the end of its life? when it no longer has any useful fuel in the star that it can keep on burning, is that the radiation pressure, which has been holding the star up throughout its life, suddenly disappears. The star collapses under gravity, and that collapse ultimately, and this is another story entirely, but that collapse leads to a supernova explosion and hence disperses the material, all of those materials, those chemical elements that have been made in the star during its lifetime, get dispersed out throughout the cosmos. So these, the fireball spreads its material out throughout the galaxy in which it takes place, and therefore future star formation sites, future planets and suns are made up of gas which has been pre-enriched by this, all of these elements that have been created in earlier generations of stars. And in that sense, we are famously all made of stardust. Okay, well, how far have we got then in our quest to understand the origin of the chemical elements? We're not doing too badly. We got the hydrogen and helium there at the left-hand end of this plot. As we move towards heavier elements, moving across this plot, we get as far as iron, and we can therefore understand all of the elements up to and around iron. What we notice, this plot has, this is relative abundance, and it's on a very logarithmic scale. So I told you already that hydrogen and helium were the most common elements in the universe. What we see is that all of those elements which are cooked up in stars then are, 10,000 times less common. But then the elements heavier than iron that we don't imagine that we cook up in stars, they're much rarer still, but they're not negligible. You might have to go down another factor of 100,000 or 1,000,000 in terms of their abundance, but they do exist. All of these other heavier elements, everything else in the bottom sort of 2/3 of the periodic table, we find all of these things, or most of them, on the Earth. And so we still have to ask the question, how did they come to be? And that was a question that was studied particularly in the 40s and 50s. A lot of that was motivated, of course, by the astrophysical puzzle, but also by the fact that the nuclear physics, of course, had taken a huge steps forward during and after the war, with the development of the bomb and with the development of nuclear reactors. And so a great deal more was understood, and many people were working on this. And the one of the most significant, certainly, researchers from the astrophysical point of view was Fred Hoyle here. And what he suggested was that heavier elements might be created in stars, but the easiest way to do so was essentially to take a heavy-ish nucleus, let's say of iron, and drop neutrons into it. Why would he say that? Well, a number of reasons. One is that there are certain stages of stellar evolution where you would expect within the cores of the stars to get a certain number of free neutrons roaming around in the plasma. So there should at least be some neutrons there. The other is that neutrons, being neutral, are not going to be repelled by the positive charge of the nucleus, whereas a proton, for instance, if you had a proton wandering around, then it would be so repelled. And so we could build up heavier isotopes of iron by dropping neutrons in over some period of time. And eventually you'd get to the point where that nucleus is going to become radioactively unstable. It's going to have too many neutrons for its number of protons, and it's going to undergo most likely a beta decay process. And that will turn one of the neutrons into a proton. And therefore, at that point, you've made now one heavier element. You've moved one element up in that chain of atomic number. And you keep doing this many, many times, and eventually you can start to build up, not in great number, because it's energetically disfavored. You're not creating energy like this, but the fact that you have these neutrons floating around means it will happen from time to time, and you start to build up all of those other heavier elements. And what Hoyle and his colleagues worked out was that this is essentially a slow process, something we call the S process. And you can see it schematically illustrated here. I see my slides are somehow, well, at least in my view, I'm seeing the last slide somehow through the next slide. I don't know if that's affecting anyone else, but I apologize anyway. I don't know why that's happening, if it does affect you. So what would you expect to find in the whole distribution then of those heavier elements, the elements beyond iron, beyond the fact that they would be in diminishing number? It was realized that you would expect to see certain peaks there. Essentially, there are certain nuclei which are more stable than others. This is a quantum mechanical process, and it's complicated and still not fully understood how to model atomic nuclei using quantum mechanics. But what we can say is that there are certain what we call magic numbers of nucleons where the nucleus ends up being particularly stable. And so you can see I've listed some of there, 2, 8, 20, 28, etc. So if you have those magic numbers worth of either protons or neutrons or both, then that will give you a particularly stable nucleus, and you would expect therefore to find more of those in this whole chain of heavier elements, because it would have got sort of a bottleneck there. And sure enough, when astronomers went out and measured the abundances of heavier elements as they found them in the solar system and in other stars, they did find peaks, and some of them were at exactly what you would expect from this slow process corresponding to these magic numbers. But then you also got peaks that were offset slightly to the left of those, and that's illustrated here in this one example here, where you can see that the S process peak should be at around about barium, but there is another peak slightly to the left of it corresponding to xenon, and that's labeled R here. And so what Hoyle and his colleagues proposed in 1957 was that indeed they could understand this S process peak from these neutron capture reactions which occurred in certain stars, but it was much more speculative what was the cause of the R process peaks. What they suggested, R stood for rapid. What they suggested was that if there was an environment in which neutrons were bombarding those heavy nuclei much faster than they could decay, in other words, you had to build up a very highly radioactive nucleus before it would actually decay because the neutrons were coming in too fast, then that would lead naturally to these offset peaks. And there's another example, the so-called third peak there between platinum and lead there. And of course, that's where gold lives. So that's why if you're interested in very precious metals, then that's of particular interest to you. Okay, well, let's have a little look at an animation to see how that works. Hopefully this will go. What we have here to start with, this is a plot of proton number versus neutron number. And what this is we're imagining now that we've got some environment that is very, very rich in neutrons. You can see where we're going to go with this, because of course that's going to turn out to have something to do with a neutron star, but it's an environment that's very, very rich with neutrons. What you'd expect to find is lots of nuclei, therefore, that have far more neutrons than protons. The normal distribution of elements that we find in nature are represented by the little black dots in this figure. So they follow a curve which starts off roughly the same numbers of protons and neutrons, and then gradually bends over so that you have larger numbers of neutrons than protons, and we can basically understand the distribution of those points. But if you've had an environment that was very, very rich in neutrons, then you expect to instead have nuclei which are way over to the right, and they're represented here by that sort of colorful band. And in a moment, we're going to see how that evolves as the neutrons keep on bombarding this original distribution of nuclei. And so let's see if that works. Yes, here we go. So we're now evolving. We're imagining this situation is that this initial mixture was very hot and very dense, and it's going to kind of explode. It's going to become less hot, less dense, and gradually, therefore, those neutrons are going to be either absorbed in the nuclei, or they're going to disappear. All of those nuclei that have become very radioactive are then going to start to decay and move back towards the stable, the value of stability there. So we run it again. we'll see what happens. The sort of little vertical and horizontal bars there are those magic numbers. So those are going to represent our stable nuclei. And we can see that they sort of build up. There are intense red spots here, large numbers of nuclei, which built up at those magic numbers, but then all decayed by beta decay, which basically takes you diagonally across this diagram. So from being at a magic number location, due to the fact that you then go through a beta decay process, which takes you diagonally, it means you end up offset from where you first thought the peak would be. Okay, that's a little bit of sort of complicated, slightly complicated nuclear physics, which I sort of thought is interesting for anyone that's ever done any of this kind of thing before, and you would quite like that. If you didn't follow all that, don't worry. Bottom line is, there's this mystery of where these R process elements come from, and Hoyle and his friends said they had to come from somewhere that is very neutron rich. So where might that be? Well, okay, I already told you the answer. It might be in a neutron star. Neutron stars, you might guess from the name, are going to contain a lot of neutrons. I already said that they're extremely dense, and so to get some kind of picture of that, we can imagine a neutron star. This is obviously an artist's impression here, on some kind of scale relative to things that we know about, and we know about towns and cities. And so basically, you know, a neutron star is, you know, sort of city-sized ball of neutrons. So something that weighs around about the same mass of the sun or a bit more, compressed into a ball that is not much more than a city. We can imagine that's going to be extremely dense. Essentially, it's the same sort of density that we get in atomic nuclei. And so famously, of course, a thimbleful of neutron star material would weigh, you know, some million billion tons or something of that order. So you don't meet this sort of matter in everyday, our everyday experience. It behaves very exotically. And in particular, the gravitational field that it creates is very, very intense. And that will be part of the story going forward as well. Okay, so what are we going to do? We're going to imagine now what happens if we merge two neutron stars. We already saw one of these kind of mergers of black holes, but I said that neutron stars not quite as extreme as black holes. When they merge, because they're not confined entirely behind event horizons like black holes are, some material can escape. So despite the very intense gravitational fields, some material can escape. And this little movie, if this is an actual computer simulation, shows you that material can escape through tidal forces. As you can see, that orange stuff that's thrown out of these neutron stars, it's only a small fraction of the neutron star that gets thrown out. But material can also get thrown out as the two stars finally collide together. And indeed, you can get a certain amount of material that's sort of boiled off the system as well. And so there are different ways of getting material out of the neutron star. So the material, when it's in the neutron star, is confined by this very intense gravity. But once it comes out of the neutron stars, it's free then to expand back into being like normal matter again. And so actually, it's going to puff up very rapidly, and as we say, decompress very rapidly. And when it does that, it's going to provide this sort of environment that Hoyle had always said was likely required if we're going to create these R process elements. Now, I should say that for several decades, 50s, 60s, 70s, 80s, 90s, noughties, more or less, the favored site for R process nucleosynthesis, as it's called, was in supernovae. People didn't know where and in what circumstances it would occur within the supernovae, or at least it wasn't clear how they would actually come about. But that was the best guess. We knew that supernovae occurred. We knew that they were extreme objects. The supposition was that in the process of a supernova explosion, this density of neutrons might be created somewhere and lead to the production of our process elements. And that's still a possibility. But it was also proposed back in the 70s that maybe another possibility was in a system like this, where you rip material out of a neutron star because it's either combined with another neutron star or with a black hole, and the material that's been pulled out decompresses and creates this right conditions to create these R process elements. Okay. And indeed, because it decompresses, because it's radioactive, it's also going to power an explosion. And so I've used the same little cartoon here that we saw for the supernova explosion. In fact, we expect the explosion not to be as energetic as a supernova. So what you're going to call it, it's somewhere between a nova and a supernova. So you could call it a pretty good nova. In fact, we are still not, there's still not any very well fixed terminology in the field, but I tend to, and many of my colleagues call it a kilonova because it's something like 1,000 times the brightness of a nova. And it also has the advantage that it confuses journalists because they think you've said kilonova. And so they get very excited because they think there's going to be something about exterminating life and that sort of thing. Okay, right. Well, now, so we've now done gravitational waves. We've done the R process elements. The third part of our talk then was going to be about these short duration gamma ray bursts. And that, again, another very interesting story in its own right. Gamma ray bursts were discovered in the 1960s. They were discovered, in fact, not by astrophysical satellites, but by military satellites. These were satellites that were launched by the US in order to monitor compliance with the Nuclear Test Ban Treaty, which had decreed that you shouldn't anymore explode nuclear bombs in space. People have been doing that. It wasn't good news. It's turned out not to be good news over a long period of time because it still interferes with our satellite observations today. But it was banned in the 60s by the Test Ban Treaty. And so in order to monitor that the Russians weren't, in fact, continuing to test their bombs in space, the Americans launched this series of satellites called Velar. There were a whole bunch of them. And they were, in a sense, like glorified Geiger counters. They were going to detect the radiation that would be produced by nuclear tests in space. And the characteristic that you expected was a very short flash of gamma rays. That would be the signature that you were looking for. And in fact, what was found was not a very short flash of gamma rays, but a rather longer flash of gamma rays. So in the late 60s, several times these satellites triggered, and each of them triggered so that you knew it was a real thing, on some source of gamma rays. And when you tried to figure out where they were coming from, all you could do was rule out the obvious things. You could rule out that they were coming from nearby the Earth. You could rule out they were coming from the sun or other objects in the solar system. But beyond that, it wasn't clear where they were coming from. The durations, there's a light curve here, as it's called, a sort of counts versus time curve on this graph. And that shows this particular one lasted, 5 to 10 seconds. But in some cases, they lasted many hundreds of seconds, in some cases less than a second. And we continued to work on these gamma ray bursts over many years, built up large statistics, but in fact, it still remained a very big puzzle, certainly through into the 90s and indeed up until fairly recent times as to what created these gamma ray bursts. One of the big clues that was found fairly early on in the 80s was that they did seem to split into two camps. So if you plotted the duration of the gamma ray emission, that's on the x-axis of this graph here, against what's called the spectral hardness, which basically tells you how were the gamma rays particularly high energy gamma rays, or were they not so high energy gamma rays? What you found was you ended up with these two groups, the so-called longer and softer. Oops, sorry, I thought that animated again. It doesn't. Longer and softer class towards the right, and then the shorter and harder class towards the left. And roughly speaking, the short and hard ones, hard meaning the higher energy gamma rays, the short and hard ones are the ones below about 2 seconds duration, and the long and the soft ones are ones greater than 2 second duration. Now, the long ones, we solved the puzzle of their origin really in the late 90s, early noughties, and we discovered that they came from certain kinds of supernovae. The short duration gamma ray bursts, they've been a much longer and more difficult puzzle to solve, as I will describe. But let me first of all tell you what we have learned from all our studies of gamma ray bursts in terms of what is actually giving rise to the emission, because it's very interesting and very exotic. Turns out in order to get this amount of intensity, given that, and something I didn't say, but what we found when we eventually managed to pinpoint some of these gamma ray bursts on the sky, something that you couldn't do with gamma rays, you needed other forms of light. But once we'd done that, we realized that they were coming from distant galaxies. So they're very far away, which means they're very, very powerful. And in order to understand the radiation that we saw, we concluded that the emission must be produced from jets of material that have been ejected from something at very high velocities. And by very high velocities, we mean 99.999% the speed of light. And they must give rise to radiation, which is of an intensity that is something like 10 to the 18 times that of the sun, something of that sort of order. So incredibly powerful, incredibly violent, and incredibly fast moving material that has given rise to these flashes of gamma rays. So that's all tremendously interesting in its own right, but in a sense that's a bit of a tangential story for our purposes tonight. But it still raises the question, if massive stars are producing the long duration gamma ray bursts, what is producing the short duration gamma ray bursts? For a long time, people had speculated that neutron stars might be involved. In fact, even before it was known that gamma ray bursts came from beyond our galaxy, from distant galaxies, people speculated that neutron stars generically might be a good place to look for the progenitors of gamma ray bursts. And the reason has to do with those intense gravitational fields that we spoke about. So picture here this cartoon, we have a little neutron star there, and we're going to imagine dropping a P onto that neutron star from some moderate height above it. And so we drop our P onto the neutron star, and it arrives with how much kinetic energy? Well, a kinetic energy that's roughly equivalent to an atomic bomb's worth of kinetic energy. So that is entirely thanks to this very intense gravitational field. Obviously, the gravitational field, the amount of energy, depends on the mass of the object that we're dropping and the strength of the gravitational field, which is determined by the mass of the neutron star and its radius. And because the mass is high and the radius is low, that means that plug all the numbers in, you get this incredible amount of energy, whatever you drop onto a neutron star. And so it was already a very obvious place to look if you wanted to create large amounts of high energy radiation. And once you realize that these things are coming from very distant galaxies, it means you've got to drop something pretty heavy onto your neutron star. Well, what could be heavier than another neutron star? So it's the same game again. We've already played it. We said this might be where the R-process elements are being formed. Maybe it's also the system that produces short duration gamma ray bursts. So I'll run this movie again, just so we can have a look at it. This, of course, is not a simulation, unlike the previous one. This is just an artist's impression, but we can imagine these two neutron stars getting closer and closer together in their final moments. They're going to touch. This is meant to indicate a magnetic field, which is likely to be spiraling in as well as these neutron stars merge. And what we saw there was that may, and we don't know exactly how, but it's reasonable to suppose that that can create our two jets there. And if we happen to be looking down one of the jets, then we see the flash of gamma rays, which is our short duration gamma ray burst. Okay, so that was the idea. That's been a favored sort of idea now for quite a long period of time. The question was, could we prove it? Could we find any evidence that connected these different strands of this story together? And that evidence really came about in 2013 for the first time, where a short duration gamma ray burst was found, in fact, by NASA's SWIFT satellite. We very quickly identified what we call the afterglow, which is essentially the X-ray and the optical light associated with the sort of fading ember of the remnant once it's merged to form whatever it forms. The jet comes out, and it's really the fading ember of the jet that we see as the afterglow. And we found that it had come from this galaxy here that you can see in the middle of the white box there. So that galaxy is, a third of the way across the observable universe. So it's not in our back door. And so we needed the Hubble Space Telescope to get a good view of it. And we observed with the Hubble Space Telescope essentially a week after the short duration gamma ray burst had gone off, and then about a month or so later. And it wasn't easy to analyze this data. So there's been a great deal of discussion that has taken place on the basis of this, really just this one image. You can see the one that's labeled June the 13th there. And at the end of the little arrow, what you notice is that there's maybe an orangish blob. So these aren't very nice color pictures because we only had 2 filters. So you can't make a nice looking color picture, but you can see the reddish bits of the galaxy and the bluish bits of the galaxy. And you can see that there's a sort of reddish blob at the end of the arrow there on June the 13th at exactly the location where the GRB had occurred. But you can see that by July the 3rd, that reddish blob has disappeared. Now, you might turn around and say to me, could that not be the afterglow, the thing that you said gave rise to optical light? Could that not be the afterglow? The answer is that we monitored the afterglow very carefully, and that seemed to have already faded away several days earlier. It faded into nothingness. And so it looked as if this was light that was now appearing again following the gamma ray burst having faded away. And that is exactly what you predict should be the case if a kilonova explosion was also taking place, that the jet was going out very fast, produced a very short-lived gamma ray burst. The kilonova was taking place from those merged neutron stars due to the material that was thrown out of them. And the kilonova is a fundamentally slower kind of explosion, starts off faint, rises to a peak in brightness after a few days, and then fades away again. So it's exactly as predicted for a kilonova. It was also the right kind of radiation that one predicts for a kilonova, which you predict should actually give rise mainly to sort of near what we call near infrared light. And so these pictures were in fact taken in near infrared light rather than optical light. And so everything about it really was pretty much consistent with what we predicted for a kilonova. And this was the first time that had been seen. These 2 events coincident, a short duration gamma ray burst and then this light, which seemed to be from this slower kilonova explosion. So that was a big deal. That was, we thought at the time, very much, put the nail in the coffin of this problem, because we'd been worrying about this for many years, in fact, how to tie these things together, and it looked as if that had finally happened. But we were also very excited because we knew that the new generation of gravitational wave detectors were coming online. We were very interested in the possibility that they would detect merging neutron stars, and we would really like to detect electromagnetic light from those mergers. You don't tend to get electromagnetic light from binary black hole mergers because they're black, but you do from mergers involving neutron stars. And of course, if the short duration gamma ray bursts are examples of the electromagnetic light that can be produced by such a merger, then you could look for those. But we also said that you only see the short duration gamma ray burst if the jet is pointing at you. And so the nice thing about this discovery was that if it confirmed that kilonovae were also produced by these binary mergers, it meant that in the future, should you detect some gravitational waves from systems like this, then there was a much better chance of you seeing a kilonova because of the fact that its light was emitted isotropically. So that brings us on to 2017, the famous first instance of a binary neutron star merger seen by gravitational waves. So I'll again run this again. So this was 2 years after the first gravitational wave discoveries of binary black holes, and this was the first case where the gravitational wave data suggested that you were seeing neutron stars instead of black holes. So the signal is rather different. We're getting a sound effect going along with it, which shows the merger. And then you've got that little pink graph as well. And that was what was being seen by the gamma ray satellite Fermi there. And so what that tells you is that there was nothing much happening in the gamma rays up until about 2 seconds after the merger, and then suddenly there was a flash of gamma rays. In other words, a short duration gamma ray burst. Now, it was an unusual short duration gamma ray burst. It was one that was much fainter than we would normally expect to see, because this was a very nearby system, and we would expect to see a much brighter short duration gamma ray burst had we been really looking right down that jet that we've spoken about. What we speculate is, and there's quite good evidence that this is the correct picture, is that we were looking at something like 20 degrees off the jet, but essentially there was enough gamma rays still produced coming in our direction that we still saw this sort of faint flash of gamma rays, even though we didn't see the full short duration gamma ray burst fireworks that we would have if we'd have just been 20 degrees over. So that was very spectacular. And this event took place at a time when the gravitational wave communities were still quite secretive about their discoveries. And so they only let a certain, I'll say, select group of astronomers in on this discovery who could then go off and make observations of possibly look for a kilonova associated with this event. Now, when I say a select group, I think people estimated this turned out to be a select group that was about 10% of all the professional astronomers in the world by the end of it. But nonetheless, we all tried to keep it very secret for a couple of months. And what did we find? Well, the finding wasn't so easy. So although Fermi detected those gamma rays, that in fact gives you only a very poor localization on the sky. So it didn't help much. Analysis of the gravitational wave data, thanks largely to the fact that we now had the European detector online as well as the two American ones, gave a much smaller region on the sky for us to search in. It's illustrated here by that green ellipse. But despite that, within that region, there are still quite a lot of nearby galaxies to look in, but it turned out this was a tractable problem, and a whole bunch of groups around the world essentially all made the discovery at very much the same time. And the ones I was involved with are illustrated there, but I'll show you my cartoon, which I still think is the best movie sequence that was made of the kilonova. So let me explain what we're seeing here. So the big white thing in the middle is the host galaxy. It's a big elliptical galaxy in which this merging neutron star event took place. And what we see in the movie is a time-lapse movie. It's over several weeks, 3 or 4 weeks. It's going to rotate back to the beginning and repeat again. And so you can see there that when the merger occurred, you got this short flash. The kilonova lit up very quickly, very blue, in fact, to start with, but then took on this more expected redder sort of behavior, turned bright in the infrared colors instead, and then finally faded away altogether. So that was very interesting. It confirmed what we'd expected. It also showed that there was actually a bit of a mixture in terms of the material that was ejected from the neutron star. So, some of it was such that it more naturally gave rise to optical light rather than infrared light, but that only dominated in that first day or so. And after that, the thing became quite red, as we see there. Behavior that's very different from a supernova, for example. So if it had just happened to be that there'd been a supernova going off in this galaxy, it would have looked really very different from that. And so we were really confident that indeed we'd got the right thing. We're really confident as well because it's sort of essentially following the predictions that had been made that this kilonova indeed is a place where this heavy, this creation of heavy elements is taking place. And so what are the consequences of that? Well, one of the consequences is that Wikipedia has changed its article on our process elements. So just, 5 or 6 years ago, if you'd looked on that article, you'd have seen that all of the purple things here, which are the R process elements, and some elements are a mixture of R process and S process. But if you'd have looked at this diagram of the periodic table a few years ago, it would have had those purple elements listed as being produced in supernovae, and it now says in merging neutron stars. Of course, we still don't, strictly speaking, know this is true. We're pretty confident that merging neutron stars are creating some of these elements. What we're not entirely confident of is that there are not other mechanisms, other places in the universe that also create our process elements. And so that's a a research project that will probably take us on another 2 or 3 decades to establish that. And so in conclusion then, we're all not only made of stardust, but rather nicely, we're also made of neutron star dust as well. So just to finish and bring you slightly up to date. So that all happened now about 5 years ago, and you might say, what's been the great progress since then? Well, 3 people got the Nobel Prize for the discovery of gravitational waves, and we might imagine them having this conversation. So now we know where all the heavy elements come from. Well, it's certainly neutron stars, as I've said, make some, but we need to really assess that budget to be adding up all these neutron stars, figuring out how much material each of them is throwing out, and whether that can explain all of the R process elements that we find in nature. And unfortunately, that's proven to be a hard thing to do. We were very lucky. Many of us realized this in 2017 to get such a brilliant and well-studied and nearby example. In the whole gravitational wave run in 2019 and 2020, we found no further examples. There are 2 or 3 other cases where it looked as if systems involving neutron stars had merged, but they were much further away and with much worse sky localizations. And so although we made sort of heroic efforts to search for kilonovae in those cases, we never found anything that looked very convincing. And so this is telling us, I think, again, what some of us thought even 5 years ago, is that it's going to be a long process. Although we were very lucky with that first one, it's going to be a long process before we start to really nail down the physics and the behavior of these events. And finally, I'll just comment that, that there was a Scottish scientist, Ron Drever, who very sadly died just before all of these breakthroughs, just before the announcement of the Nobel Prize as well. He'd been sort of slated as to be likely to be one of the 3 who would have been given the Nobel Prize, but of course they're not awarded posthumously, and so his place was otherwise taken. And then I'll just finish off with this movie that was created, just showing with a little bit of fancy music what we think we saw then in the 2017 event. And you can see the jets of material. You can see this complicated explosion that we now think was the kilonova. The jets, as they impact the tenuous gas surrounding the event, give rise to an afterglow, which we did see. And so that was all supposed to be illustrated there with that fancy animation. And I'm done with that. What am I doing? Okay, not too bad. I haven't kept you unduly long.
Niall, thank you very much indeed. Beautifully timed. I hope people can hear me. A question: what's the sort of decay rate of a kilonova by comparison with nova and supernova? I got a feel from your diagrams, but is there a sort of, is it 5 days, 10 days?
This is a fine and perfectly reasonable question, but it's one that is not at all easy to answer, and for various reasons. One is that there are many elements that are involved in powering kilonovae, unlike supernovae, where you know that it's starting with nickel 56, etc., yeah, and going down the various decay chains from that. That's not the case here. So you have potentially many different elements. They are elements which are far from equilibrium, and so we don't have a great understanding of the nuclear physics even involved. And then you've also got the complex, very complex atomic physics, which is taking place as well, that is leading to the radiation being obviously, emitted with and absorbed by electron transitions in these very complicated many electron atoms. So the net result is that it's a very complicated thing to model, and the modelers have made great progress, no doubt about it, over the last 10 years, before and after we made the observations. But particularly the later time behavior is the least certain. And so it's a bit hard to say. I would say that this, from the 1708-17 experience, it remained bright for longer than was expected, and all of the original fits to the data failed to explain the later time behavior. And now, of course, people have improved their models, and so they're starting to get better fits there, and so you can begin to fit it. But yeah, not an easy question to answer.
A question from John Axtell. Fascinating talk, many thanks. Will the JWST be used to hunt for more kilonovae?
Okay, again, another very pertinent question, with James Webb now up and apparently working very well. It's obviously really lends itself to so many things. Definitely would really lend itself to studying kilonovae, particularly in the infrared, particularly beyond the near infrared that we can study reasonably well from the ground. It becomes very hard from the ground beyond about 2.5 microns in wavelength, and a lot of the action in terms of the emission from the kilonovae could well be taking place at longer wavelengths, exactly where James Webb has vastly more power than all of its predecessors, and even more compared to anything that we can do from the ground. So in principle, it's a very powerful tool. In practice, there are some impediments, and one is that they have been, I think, to the disappointment of many people, ended up being very conservative about using James Webb for target of opportunity observations, which is, in other words, unexpected events. For years and years, for decades, the Hubble was very conservative. It gradually became slightly less so, for reasons which I find still, even now, slightly perplexing. I think a lot of sort of institutional inertia in the system that made them reluctant to really work on improving the Hubble's ability to respond to new events. But for many years, I would ask this question of colleagues at the Space Telescope Science Institute, for example, and they would always say, for many years, they would say, yes, but James Webb, we're really making every effort to make sure that it'll be much more flexible than Hubble and will be able to respond quickly. And then as we got closer and closer to the actual launch and the first round of proposals were made, suddenly it went back to being a very conservative approach to doing these things. So the bottom line is, it has been allocated time already on the James Webb. If a kilonova, a good enough kilonova occurs, it will be observed. And because we don't expect to get a high rate of these things, as I've already explained to you, then they're rare in the nearby universe. And so they're hard to find. And therefore, I think the number that we will get even over the next decade is still probably only going to be a handful. And I think, that's the sort of numbers that very likely we will get James Webb observations of. Now, you did ask specifically whether it would be used to search for them. And the answer there is probably not really, or pretty unlikely, in the sense that James Webb, of course, like Hubble, has a pretty small field of view. So it's really not good for looking for something that you don't already know exactly where it is. And so most likely the hunting will still take place using large wide field ground-based telescopes, possibly complemented with high energy satellites that might detect X-rays, for instance, from the jets. And those routes will be used in order to pinpoint down the location, and then James Webb hopefully will be turned on to that location to do the really detailed follow-up.
A question from Rachel. Thank you so much. That was very interesting. Out of curiosity, do you think it would be possible to use kilonovae as standard candles in the future?
Well, so I used to do a lot of work in standard candles, and I guess I have kind of high standards of my standard candles, and there are some standard candles out there which are really good, and we're familiar with them because, of course, the Cepheids famously were the original stellar standard candle, and they are really good standard candles. Type 1a supernovae, much brighter, much rarer, but brighter, seen far away, and we all know now that they are also excellent standard candles. For years, people have been attempting to turn other objects into standard candles, including gamma ray bursts. Having come from that distance scale field, I was always quite skeptical about it. No doubt, there have been some studies which, seem to have done a half decent job, but I guess I'm still fundamentally quite skeptical about it. Not to say I don't think that gamma ray bursts can be used at all as standard candles. I just don't think they're so standard. So you've got something which, is not a perfect light bulb. There's a certain amount of variation around the mean, and that unfortunately really spoils that for doing kind of cosmological work we'd like to do. It doesn't help you at all. Now, kilonovae are a different matter. Already, indeed, people have speculated that they might be. I tend to think not. I tend to think that they're such sort of messy systems. We certainly know already from studies actually of other kilonova candidates associated with short duration gamma ray bursts. There have now been a few others found following the one in 2013. We know there's quite a range in brightness. So we certainly know they're not standard. So what you'd be having to look for instead is some way of kind of standardizing them, whereby you look for some other property that correlates with the faint ones and the bright ones, and therefore tells you whether you're looking at a faint or a bright kilonova. I mean, no doubt people will endeavor to do it. I don't imagine they're going to have much fortune. What I will say, though, is that the whole game that we're playing here does lend itself to a different or new approach to this whole distance scale business, not from the standard candles so much as the so-called standard sirens, which is the name we give to the distance that you get from the gravitational wave itself. So the gravitational wave observations give you a distance, which in the future with better and better detectors is going to become more and more precise. And what they don't do, though, is give you a redshift. So if you're interested in for instance, getting a better value for the Hubble constant, you would like to know both the distance and the redshift. And that's where these kind of objects come in, because if the gravitational waves in the future can give much more precise distances, and we can see a kilonova and therefore take a spectrum and find a redshift, then we can put those two things together and get good new estimates of the Hubble constant that way. So there's definitely interest in that area, but I rather doubt that it'll come from standard kilonovae.
Question from Andy Andrews. Do neutron stars evaporate like black holes? And if so, what happens to them at or near the end?
Okay, another interesting question. They don't evaporate like black holes, which, as many of you probably know, the evaporation of a black hole is a very exotic physics in its own right, having to do with the behavior of quantum mechanics as applied to the space very close to the event horizon, leading to the emission of light even from something that is notionally black. Now, that wouldn't take place in a neutron star. In a sense, one has to understand as well that in realistic terms, any given black hole in an astrophysical situation is likely to be absorbing more light and mass and energy than it is emitting. So the actual evaporation is going to be a very odd situation in our present universe. May happen more commonly in the very far future. In terms of neutron stars, again, the situation is they're rather more likely to absorb matter than emit it, but there certainly are there are mechanisms which take place on neutron stars, which themselves are super interesting, which can give rise to at least the emission of plumes of plasma. One of them has to do, and I mention this really just because it's so crazy and interesting, has to do with the very intense magnetic fields, which fairly often characterize neutron stars, particularly very young ones, which have not been formed very long. And so these magnetic fields are the most powerful magnetic fields that we know of in nature. And they can be so incredibly powerful that it's thought that in some circumstances they can even split a neutron star and rotate it and then reconfigure it again. So, you know, the neutron star is a pretty stiff thing, as you can imagine, but these magnetic fields are so immense that they it's thought have that capability, or certainly of reconfiguring the neutron star in some largish scale. And those processes, for example, as you can imagine, certainly can give rise to ejection of a certain amount of energy, which you know, can produce a sort of fireball as well. But yeah, for the most part, material that once it's on a neutron star is pretty well stuck to it. So it has to be a rather dramatic thing to get material out of a neutron star. Where one of the sort of analogies or examples, in the sense that I like to give, if you were trying to imagine, you know, just how intense is that gravitational field on a neutron star. I ask you to imagine you're standing on a neutron star, which isn't necessarily a very wise thing to do, but you decide to stand down and you drop something, you know, let's say it's a tennis ball or something, to test the strength of the gravitational field. What you find is that by the time the tennis ball reaches the surface of the neutron star, it's moving at several million miles per hour. So the intensity of the gravitational field is such that the acceleration is incredible. And yeah, stuff, once it's reached that stage, doesn't easily get back up again.
And the directionality of GRBs, is that mediated by magnetic forces?
Right. Okay. So again, this is not fully understood. So there's still a lot of work, and has been, you know, for a long time. To be honest, in general, for astrophysical jets, which we find in many places in astrophysics, we find jets are produced. The jets produced in gamma ray bursts are the most powerful and fast-moving jets that we know of. But what ejects the material in those rather narrow jets, few degrees across, is what we think. We don't exactly know, but the ingredients are exactly strong magnetic fields and rapid rotation. And so, you know, it's easy enough to imagine the field lines of the magnetic field as being like elastic bands. And indeed, that's, you know, that's not a bad picture to carry around with you, because they have a sort of tension. And so you can imagine that as the two neutron stars and their magnetic fields are wrapping around each other, that you could coil up those elastic bands. So that creates a sort of funnel of magnetism, which both in and of itself can eject energy, in fact, magnetic energy up in that direction, or it can accelerate particles as well. And so the basis of that is sort of understood. The details and really creating such fast moving jets carrying so much energy is not well understood.
Yep. Any other questions? Niall, thank you so much for a stunning, full, rich, and extraordinarily entertaining talk. Thank you on behalf of GAS.
Oh, you're very welcome. Glad you enjoyed it.
And all the very best. Look forward to hearing more from you in the future.
Yes, indeed. Yes. Well, and best wishes for your observations and some clear skies and all that stuff. Yeah.
So on May the 5th, we've got Kate Womack, who's a colleague of Brad Gibson, talking about the cosmological origins of the chemical elements, which I realize might have some parallel components to what Niall has just talked about. On June the 2nd, Paul Daniels is going to talk about Lagrange points, which have become particularly of interest with the James Webb. Jovian and lunar orbits and the Kordylewski clouds. And then on June the 7th, we're going to have our AGM, and the particular attraction for that. Hopefully people will want to participate in the AGM, but nevertheless, in addition, Philip Harris, one of our own members, is going to talk more about neutrinos